Now, in the previous session, we were talking about the problem that arises in perturbation theory when you have degeneracy. In other words, when you have two or more eigenfunctions that have the same eigenvalue. And that led to a problem because we had a formula in the previous session for the corrected, the first order correction of the eigenfunction, and it involved a formula where the denominator of one of the terms was a difference between two energies, energy eigenvalues, Em and En. But if it happens that the Um, the eigenfunctions that correspond to those eigenvalues, so if the Um and the Un are degenerate, in other words, they have the same eigenvalue, so that Em equals the En, then you've got a zero in the denominator. You're dividing by zero, and that's a no-no in physics. So what you do now, it's a problem, a conceptual problem. Now, Davies and Betts, they state that there is an easy solution to it. Now, the details that they gave were pretty skimpy, so not easy to follow. So, in certain parts in this session, I've actually quoted them. Put like down here. I put actual quotes from the text. So hopefully that will be enough if you have a more background that I've been giving you to understand what they're talking about. But if you don't, it's not clear. You won't have enough details to understand what they're saying. Right? So be conscious that in perturbation theory there is a problem when you have degeneracy. You get this blow up when a denominator goes zero, when the Em and the En become equal, and you're dividing by zero. But they claim that you can get around this problem because put it this way: put all the degenerate eigenstates in a bunch, and you can form a linear combination of them, and that linear combination will also be degenerate. It'll have the same eigenvalue as all the other degenerate eigenfunctions. So you can form a linear combination of those degenerate eigenfunctions. Now, doing that, that allows you to diagonalize. Now, if you don't know what I'm talking about, don't worry. But if you do, you may go, oh, that's how they did it. Right. So you need to know enough linear algebra to understand what diagonalizing a matrix means. It just means constructing a matrix that's diagonal. In other words, the whole matrix has zero elements except down the northwest southeast diagonal. Right? Those elements, some of them, are non-zero. Right? It's a diagonal matrix. So you can construct a diagonal matrix from the what do we call it now? 2 sessions ago we had a formula for the first order correction of the eigenenergies, and it was the expectation value of h hat dashed. Remember? So I'm looking at it. I mean, I can see it. You can't. So 2 sessions ago, we found a formula, an expression for the first order correction of the Hamiltonian, or the energy eigenvalue. So it was bra um naught times the operator H hat dashed ket UN naught. So in the bra you had a UM, in the ket you had a UN. So that gets defined as the mth row, nth column of a matrix. Right. So I'm assuming, from it's been a while since I've done linear algebra, but you can diagonalize that matrix by appropriate use of the UMs and the UNs. You can take linear combinations of the bra, the terms in the bra. You take your degenerate eigenfunctions, you make a linear combination of them, you plug them into this MN matrix, and hence what? So you diagonalize this matrix, and that way the problem disappears. Now there's the hand-wavy fuzzy part that I didn't follow too well, because there are not enough details. Right? Now if you go to the previous session, there was we had an expression for the first order correction to the eigenfunctions, so the UN1, and they involved sigma of HMN dashed divided by EN naught minus EM naught. Now I'm guessing from what you're saying here, select the linear combination, these are the degenerate eigenfunctions, right, that diagonalizes the degenerate submatrix of the matrix H dashed Mn. So I'm guessing the H dash Mn, that's now been diagonalized, and so when m is not equal to n, it becomes 0, and hence the problem disappears. That's what I'm assuming they're saying, but there are not enough details. So again, feeling rather antsy. I appreciate there has to be, in an introductory course where you're giving an overview, flying over the icebergs, giving an overview of the field, the subject. There have to be times when the author is forced to do what I call ICBST. It can be shown that you just get things thrown at you, right? So I appreciate that. It's pretty well unavoidable. I don't like it. A lot of people don't like it, but how can you avoid it? All right. So next topic. So the three major topics in this chapter. The first two are on perturbation theory, and the third one is on something called variational techniques. Now this is now the beginning of the second part, which is on applications of perturbation theory. So in this session I can do the first one fairly easily, and I can start on the second one, and then I run out of board. So we'll turn around and talk about the first one. The first one's just called the anharmonic, or the non-harmonic oscillators. Now, we did quite a bit in earlier lectures on the harmonic oscillator, or the simple harmonic oscillator, the SHO, simple harmonic oscillator. And the solutions to that are exact. Right? So you have a nice tidy approach. We can find corrections to the eigenenergies, the eigenvalues. We know, or we're given what H dashed is, the perturbing term in the Hamiltonian, and we know the unperturbed eigenfunctions because we solved for those. We did that way back when we were talking about the simple harmonic oscillator. So the solution, the eigenfunctions, the U naught, the UN naught, we know those, and they're nice tidy terms, they're exact solutions. for this problem, the unperturbed system, which is your simple harmonic oscillator. Right? Now, we're just given in this problem, this example, this application of perturbation theory, we're just given that your H dashed, your perturbing term in the Hamiltonian, is just simply alpha x to the fourth. Now, this alpha doesn't mean proportional, it doesn't mean the fine structure constant, it's just a constant, right? So, lots of alphas, and you have to look at the context to see what alpha means. Well, in this case, just a constant. Right? So you've got an extra term in your Hamiltonian, your H0 hat, and it's just alpha x to the fourth. Okay, so look on that as an extra potential, V, in your Hamiltonian. Hamiltonians in classical mechanics usually just kinetic energy terms plus potential energy terms. This is quantum mechanics. So just say this is an extra term. This is your H dashed in your V, or the potential in your Hamiltonian. Right? Now, so we'll calculate the first order correction to the ground state